We all remember circles, ellipses, parabolas, and hyperbolas, right? From, math class. Maybe not so fondly for some of us.
Yeah.
But stick with me here. Because what if I told you that these shapes aren't just some abstract math equations? They actually pop up in the real world in some pretty wild ways. And even wilder, they all come from the same, origin story.
Yeah, that's a great point. It is kind of mind-blowing when you think about it. All these different curves, we call them conic sections, by the way, they all come from doing something pretty simple. Just slicing a cone. A specific type of cone, but still just slicing a cone with a plane.
Okay, so right off the bat, we need to unpack this cone business. And that's what this deep dive is all about, right? We're here to really get into the nitty-gritty of these conic sections. We're talking circles, ellipses, parabolas, and hyperbolas, what they are, what makes them special, and yeah, those real-world connections you mentioned. We're going to be pulling all that from the source material we have for this episode.
Absolutely. And don't worry if you haven't thought about math in a while. We'll keep it clear and avoid any unnecessary jargon. We're here to make this stuff understandable.
Perfect. So let's get back to that cone. What exactly are we picturing here?
Okay, imagine a perfectly straight vertical line. That's our axis. Now, picture another line that intersects it at one point at an angle. We'll call that point the vertex. If you spin that second line around the vertical axis, keeping that angle the same the whole time, the path it traces out will create the surface of a cone.
Okay, I think I'm getting it. Like if you had a stick and you spun it around another stick that it's touching at one end, the first stick would create that cone shape.
Exactly, you got it. And that point where they meet, that vertex, actually creates two cones, mirror images of each other, connected at their tips and extending infinitely in both directions. We call those two parts the naps of the cone.
Naps, got it. So I'm still not quite seeing how slicing this thing gives us all those different shapes.
All right, well, that's where our plane comes in. A flat plane, like a sheet of paper. It's all about how this plane cuts through the cone, at what angle and where exactly it slices through. That's what determines which conic section we end up with. Let's say the angle between our plane and the vertical axis of the cone is, we'll call it beta, the Greek letter buck.
So different angles, different shapes. That's the basic idea.
You got it. If your plane cuts straight across just one of the naps, perfectly horizontally, then our beta angle is 90 degrees. And guess what? The shape you get where the plane intersects the cone, that's a circle. You can actually see this in figure 11.4 of the source material. Kind of like slicing a loaf of bread straight across, you get a round slice.
Okay, that makes sense. Level cut, round shape.
Yeah.
So what if we tilt the cut a little?
If we tilt the plane so that the angle beta is somewhere between, well, that angle of the cone itself, which we'll call alpha, and 90 degrees, and it still only cuts through one nap, then bam, we've got ourselves an ellipse. Figure 11.5 in the source shows this visually. So you can think of a circle as just a special case of the ellipse. It's what you get when the plane is perfectly horizontal.
Interesting. So a circle is a level cut. A tilted cut gives us an ellipse.
Yeah.
What happens if we tilt it even more? What if that beta angle, the angle of our plane, is the same as the angle of the cone itself, alpha?
Okay, now imagine the plane running parallel to the side of the cone, still just cutting through one nap, but the shape we get is now a parabola. You can see this in figure 11.6. Like, picture the plane just kind of skimming along the surface of the cone.
Circle, ellipse, parabola. We're on a roll. What's the last one?
The last one, the hyperbola, that's where it gets really interesting. Now we need our plane to cut through both naps of the cone. This happens when the beta angle is between 0 degrees, or horizontal, and alpha, the angle of the cone. Take a look at figure 11.7 to visualize this. That slice, it gives us two separate curves, kind of mirror images of each other.
So it's a cut that goes in one side and comes out the other. Makes sense why the hyperbola has those two distinct parts.
Exactly.
So we've got our four main conic sections, but the source also mentions these degenerate cases. What's going on there? What makes them different?
These degenerate cases, they happen when our cutting plane doesn't just slice through the cone, but actually hits it right at the vertex. Remember, that's the point where the two naps meet. So instead of getting a nice smooth curve, we end up with something simpler.
Simply like how? What kind of shapes are we talking about?
Okay, so if the angle beta, our plane's angle, is between alpha, the cone's angle, and 90 degrees, which means it's steeper than the cone side but not horizontal, and it goes right through the vertex, then all we get is a single point. Just the vertex itself, actually. That's shown in figure 11.8.
A single point, huh? Makes sense, I guess. It's like if you could balance a piece of paper perfectly on the very tip of a cone.
Exactly. Now, if beta equals alpha, meaning the plane is lined up perfectly with one of the lines that generate the cone, then the intersection is a straight line. You can see this in figure 11.9. And this is considered the degenerate case of a parabola.
Okay, last degenerate case. Got to be something good, right?
When beta is between 0 and alpha, so the plane is less steep than the cone side, but still hits the vertex, we get two straight lines that intersect right at that vertex. This one, it's the degenerate case of a hyperbola. Figure 11.10 shows what this looks like.
Gotcha. So even these simpler shapes come from that same basic cone idea. Really drives home how important that starting shape is.
Exactly. Now that we've kind of gotten a feel for how these shapes come about, why don't we zoom in on each one? Let's start with the one everyone knows, the circle.
Yeah, the circle. We all know what it looks like. But what's the formal mathematical definition? Like, how do we define it precisely?
So a circle is defined as the set of all points in a plane that are the same distance away from one specific point in that plane. That special point, that's the center of the circle. And that constant distance, that's the radius, of course. Figure 11.11 shows this nicely. And the equation of a circle, it's basically just a translation of this definition into mass language. Every point that fits that equation has to be that same distance from the center.
Center and radius. Got it. But how do we go from that definition to an actual equation?
Well, that's where the distance formula comes in. Say the center of our circle is at a point with coordinates on a graph, and any point on the circle itself has coordinates xy. The distance between those 2 points, hk and xy, has to always be the same. It has to equal the radius, r.
Yeah, and the distance formula tells us how to find that distance, right? It's the square root of the difference in x coordinates squared plus the difference in y coordinates squared.
You got it. So if we set that distance equal to r, our radius, we get the equation, xh tro plus ykr. To make it a bit cleaner, we square both sides to get rid of the square root. And there you have it, xh plus yk shri equals r for rho. That's the standard equation of a circle. Figure 11.12 shows this whole derivation visually.
So if the center of the circle is right at the origin of our graph at 0, 0,
Yeah.
that equation becomes a lot simpler, right? Just x squared plus y equals r read.
Exactly. Now let's get our hands dirty with some actual examples from the source material just to see how this works in practice.
Perfect. Example 2 asks us to find the equation of a circle with its center at -3, 2, and a radius of 4.
Okay, so we just plug those values into our standard equation. Up some x free plus y quadra is orbit. In this case, h is mother's 3, k is 2, and r is 4. So we get x neck is 3 plus y 2 put ladder's 4. Simplify that a bit, and it becomes x plus 3 para plus y 2 ladders at 16.
Easy peasy when you have the center and radius. What if we're given the equation and need to figure out the center and radius?
That's where we use a handy little trick called completing the square. Example 3 gives us this equation, x sepshot plus y plus 8x plus 10y8 equals 0. And we want to rearrange it to look like our standard form, xh plus yk equals r roll.
Oh yeah, completing the square, I kind of remember that. Involves like grouping the x terms and the y terms, right?
Exactly. So first we rewrite it like this, xx plus 8x plus y plus 10y equals 8. Now for each of those groups in parentheses, we want to add a number that will turn it into what's called a perfect square trinomial. For the x terms, x epsilon plus 8x, we take half of the coefficients of x, which is 8, so half is 4. Then we square it, 4 plus 7, 16, and add that to both sides of the equation. Same idea for the y terms. Y plus 10y. Half of 10 is 5. 5 squared is 25. So we add 25 to both sides.
So the equation becomes x sexol plus 8x plus 16 plus alaz plus 10o plus 25 equals 8 plus 16 plus 25.
Exactly. Now those groups in the parentheses, they're perfect squares. X plus 8x plus 16 becomes x plus 4 value, and y plus 10y plus 25 becomes y plus 5 value, and 8 plus 16 plus 25 on the right side, that equals 49. So boom, our equation in standard form is x plus 4 metal plus y plus 5 value equals 49.
Nice. So now it's easy to see. Comparing this to xh plus y equals or, we can see that h is -4, k is -5, and r is 49. So our center is at -4 and nice 5, and the radius is the square root of 49, which is 7.
You got it. Let's do one more example. This one's a little trickier. Example 4 says we need to find the equation of a circle that passes through the points 2, 9 is 2, and 3, 4, and whose center is on the line x plus y equals 2.
All right, so this one gives us a few different pieces of information we got to put together.
Exactly. We start with our trusty general equation, xh plus yk r equals r. We know the circle goes through those 2 points, 2, 9 is 2, and 3, 4, so we can substitute those x and a values into the equation. That gives us 2 equations with hk and r in them. And we also know the center, x plus y, lies on the line x plus y equals 2. That gives us a third equation, h plus k equals 2.
So we have 3 equations and 3 unknowns, h, k, and r. That's solvable.
Absolutely. Solving this system of equations, which involves a bit of algebra, but we'll spare you the details, gives us these approximate values. H is zero point 0.7, K equals 1.3, and R, bottle all, is 12.58. So the equation of our circle is about make 7.7 while R plus Y 1.31 while equals 12.58.
Okay, I see how we use those geometric conditions to find the equation. The source then mentions exercise 11.1. What kind of stuff can our listeners expect there?
Exercise 11.1 gives you a bunch of problems to really test your understanding of circles. You'll be finding equations when you're given the center and radius, finding the center and radius when you're given the equation, and even finding equations based on different conditions, like points the circle passes through and where the center is located.
The big takeaway for me with circles is how that simple idea, all points being the same distance from a center, turns directly into the algebraic equation, like the language of geometry and the language of algebra are perfectly in sync.
That's a really great observation, and it brings up an interesting thought. Consider how that geometric definition so effortlessly becomes the algebraic equation. It really highlights the power of using coordinates to describe geometric shapes, doesn't it?
For sure. All right, let's move on to our next conic section, the parabola. What makes this curve special?
The parabola, well, it's all about this idea of equal distance. It's defined as the set of all points in a plane that are the same distance away from a fixed line. We call that the directrix. And a fixed point, that's the focus. Take a look at figure 11.13. It shows this visually.
So unlike the circle, with its one center point, the parabola is defined by this relationship to both a line and a point. What other key terms should we know?
So along with the directrix and focus, we have the axis of the parabola. This is the line that goes through the focus and is perpendicular to the directrix. And then there's the vertex, which is the point where the parabola itself intersects its axis. Figure 11.14 labels all these important parts.
What about that degenerate case we talked about earlier? What happens if the focus is actually on the directrix?
Good question. In that specific case, the parabola basically collapses into a straight line. It's a line that passes through the focus, which is on the directrix, and is perpendicular to the directrix.
So a straight line instead of that familiar U shape. The source mentions standard equations for parabolas. What makes them standard?
The standard equations, they're basically the simplest forms of the parabola's equation. They happen when the vertex of the parabola is at the origin, 0, 0, and the axis of symmetry is lined up with either the x-axis or the y-axis. This gives us 4 basic orientations for the parabola opening to the right, left, upwards, or downwards. You can see all 4 in figure 11.155a through d.
So the parabola can open in any direction.
Exactly. Let's take a closer look at the equation for a parabola that opens to the right, like in figure 11.15a. Here, the focus is at a, 0, where a is some positive number, and the directrix is the line x equal a.
Okay, so we've got our focus to the right of the origin and the directrix the same distance to the left.
Right. Now, let's say we have a point P with coordinates x, y that's on this parabola. Remember the definition. The distance from P to the focus, which is at A0, has to be the same as the distance from P to the directrix. The line x equals A. Figure 11.16 shows this.
So we'll need the distance formula for the distance from P in the focus and the formula for the distance from a point to a line for the distance from P to the directrix.
Precisely. So the distance from P to the focus is xa plus y0, which we can simplify to px plus y. The distance from P to the directrix is simply the absolute value of xa, which is x plus a.
Right, so we set those two distances equal to each other and then square both sides to get rid of that pesky square root.
You got it. So we have x plus y, x plus a. Squaring both sides gives us xa plus y, x plus a2. Then we just expand both sides and simplify it, and we end up with yx e 4x.
And that's our standard equation for a parabola opening to the right. What about that a value? What does that tell us?
Because a is positive in this case, the equation a equals 4x tells us that x has to be greater than or equal to 0. That means the parabola only exists on the right side of the a-axis, or on the y-axis itself. It extends forever in the first and fourth quadrants. And the positive x-axis, that's our axis of symmetry.
And those other 3 orientations, do they have similar equations?
Very similar. For a parabola opening left, the equation is ui colliquartis 4x. Upwards, it's x 4x equals 4a. And downwards, it's x 4x equals 4a. Again, you can see these in figure 11.15b through d.
Interesting how the direction it opens depends on whether x or y is squared and the sign of a. The source mentions that we're not going to deal with cases where the focus and directrix are in other positions.
That's right. We're keeping it simple here, focusing on these standard forms where the vertex is at the origin and the axis is lined up with one of the coordinate axes.
And you mentioned symmetry earlier.
Yeah, parabolas are always symmetrical with respect to their axis. So if the equation has a y, like I call 4x, then x-axis is the axis of symmetry. If it has x SOR, like x SOR of 4a, then the axis is the axis of symmetry.
And just by looking at the equation, we can tell which way it opens, right? If it's a y equation and the x term is positive, it opens right. If it's negative, it opens left. Same idea for xordered equations. Positive y term means it opens up. Negative y term means it opens down.
Exactly. Now, there's one more important feature of the parabola we should talk about, the latus rectum.
Latus rectum. Sounds kind of fancy. What is that exactly?
It's a specific line segment that's associated with a parabola. It's the line segment that's perpendicular to the axis of the parabola, goes through the focus, and has its endpoints on the parabola itself. Figure 11.17 shows this.
So it's like a line that cuts across the parabola at the level of the focus.
Yeah, in a way, it gives us a measure of how wide the parabola is at that particular point. To figure out its length, let's go back to our parabola that opens to the right. Y equals 4x. We know the focus is at A, 0, 0. And because the latus rectum goes through the focus and is perpendicular to the x-axis, which is our axis of symmetry here, the x-coordinates of its endpoints also have to be A. Take a look at figure 11.88. It helps visualize this.
Okay, so if we know the x-coordinate is A, we can plug that into our equation, y equals 4x, and find the corresponding A coordinates.
Exactly. If we substitute xa into the equation, we get y equals 4x. Then we take the square root of both sides, and we get y equals 2a. So our endpoints are a to a and a and equal 2a. And the length of that segment, well, it's the difference between those I values, 2a and equals 4a.
So the length of the latus rectum is just 4a. That's pretty neat. The source then goes through a few examples to illustrate all this.
Yeah, example 5 gives us this equation, y equals 8x, and asks us to find all the important stuff: focus, axis, directrix, and latus rectum.
So we compare that to our standard form, y equals 4x. We can see the 4a must be 8, which means a is 2.
Yep.
So the focus is at a, 0, which is 2, 0. The axis of symmetry is the x-axis, because we have y equation. The directrix is x is a, so that's x equals minus 2. And the length of the latus rectum is 4a, which is 4, 2, or 8. Figure 11.19 shows all this.
Exactly right. Now, example 6 kind of flips the script. It tells us the focus is at 2 and the directrix is x, 0 is 2, and we have to find the equation.
So knowing the focus and directrix, we can tell a is 2. And because the focus is to the right of the directrix, the parabola opens to the right. So it's got to be y is 4x, plug in a is 2, and we get y is 4, 2x, which is just all ax.
And then there's example 7, where the vertex is at 0, 0, and the focus is at 0, 2.
Because the focus is on the y-axis, we know the equation's got to be x0 equals is 4a. Since the focus is at 0, 2, a is 2. So our equation is x0 equals 4, 2, or x0 equals 8y, and this one opens upwards.
Yeah, so the location of the focus tells us whether we're dealing with an x0 equation or a y equation. Now, example 8 gives us a little word problem. Find the equation of a parabola that's symmetric about the y-axis and passes through the point 2 NASI 3.
Okay, because it's symmetric about the y-axis, it's got to be either x0, 4a, or x0 equals 4a. The point 2 NASI 3, well, that has a positive x and a negative y, so it's in the fourth quadrant. For the parabola to go through that point and be symmetric, it has to open downward. So you use the form x0 equals an apps to 4a.
Right. Now we just got to find a way. We know the point 2 NASI 3 is on the parabola, so we can substitute those values into the equation. 2 9 hen equals 4a NAS 3.
So that's 4 equals 12a, which means a is 4, 12, or 13.
And plugging that back into our equation, we get x banner 4 13y. We can simplify that to x minus 4a 3y, or 3x banner 4a 4y.
So we use the symmetry and the given point to figure out the equation. The source then mentions exercise 11.2. I'm guessing that's more practice with this kind of problem.
You got it. Exercise 11.2 has more problems where you find the focus, axis, directrix, and latus rectum when you know the equation, and vice versa, you find the equation when you're given those other properties.
What stands out to you about parabolas? For me, it's how that definition, the whole equidistant thing, creates this really elegant curve. And the latus rectum, it gives us a really direct way to understand its width at that focus point.
Yeah, great points. It makes you wonder, how does the length of the latus rectum, 4a, directly tell us the width of the parabola at the focus? If a is bigger, does the parabola open wider? Think about it.
Okay, time for the next one, the ellipse. What makes the ellipse special? What's its defining feature?
The ellipse, it's all about a constant sum of distances. It's defined as the set of all points in a plane where if you take the distances from that point to two other fixed points called the foci and add them together, you always get the same value. We usually call that constant sum 2a. Figure 11.20 shows this really well.
So it's not about equal distances like with the parabola,
Yeah.
but a constant sum of distances. And there are two foci now.
Exactly. And that constant sum 2a, it's always bigger than the distance between those two foci.
So what are the key terms for ellipses? There are probably a bunch.
Well, we already mentioned the foci. The midpoint of the line connecting them is called the center of the ellipse. The line segment that passes through the foci and has its endpoints on the ellipse is called the major axis, kind of like the longest diameter. And the line segment through the center, perpendicular to the major axis, with endpoints on the ellipse, that's the minor axis, like the shortest diameter. The endpoints of the major axis, those are the vertices of the ellipse. You can see all this in figures 11.21 and 11.22.
Major axis, minor axis. So it's
Yeah.
like the ellipse has a long radius and a short radius.
Exactly. The length of half the major axis is called the semi-major axis, and we label that A. Half the length of the minor axis is the semi-minor axis, labeled B. And the distance from the center to each focus, we call that C. Now, there's a super important relationship between these three. C codes equals ABB. Remember that minus sign, it's key for telling the difference between ellipses and hyperbolas later on.
Where does that equation, C pokey PP, come from?
If you look at figure 11.23, you'll see how it works geometrically. Take a point at one end of the major axis. The sum of its distances to the two foci is 2a, by definition. Now, if you take a point at one end of the minor axis, the distances to each focus have to be the same because of symmetry. And if you use the Pythagorean theorem, you can show that C plus B equals A pat. Rearrange that, and you get C aploin equals A bi.
Okay, I see the connection. What happens if we push the ellipse to its extremes? Like, what are the special cases?
Let's start with the case where the distance between the foci is 0, so C equals A bow. Our trusty equation CAAP tells us that AA export, which means AXB. If that happens, the two foci end up at the same point, the center, and our ellipse turns into a perfect circle. Figure 11.24 shows this. It's like a circle is just an ellipse where the two foci are the same point.
And what's the other extreme?
What if the distance to the foci, C, is equal to A? Then C fo AAB tells us that the bi has to be 0, so bi is A. Now our ellipse is squashed flat into a line segment connecting the two foci. See figure 11.25 for this one.
Wow, from a perfect circle to a straight line. That's quite a range for the ellipse. What about eccentricity? We talked about that earlier for conic sections in general.
Yeah, eccentricity, denoted by E, basically tells you how stretched out an ellipse is. It's the ratio of the distance from the center to a focus C to the length of the semi-major axis AECA. For any ellipse that's not a circle or a line segment, the eccentricity is going to be between 0 and 1. Closer to 0, it's more circular. Closer to 1, it's more elongated. And the foci, they're located a distance of A away from the center.
That makes sense. A circle with E equals 0 has its foci right on top of each other. And as E gets closer to 1, those foci move further apart, stretching the ellipse out.
Exactly. Now on to the standard equations. These equations are simplest when the center of the ellipse is at the origin, 0, 0, and the foci are either on the x-axis or the y-axis. Figure 11.26 shows both of these setups.
Let's start with the foci on the x-axis. How do we get to that standard equation?
Let's say our foci, we'll call them F1 and F2, are at C0 and C0. And let's say P with coordinates x, y is any point on the ellipse. Remember, the definition says the distances from P to the foci have to add up to that constant 2a. Using the distance formula, that gives us x plus c plus y plus y plus y plus 2a.
Yikes, that's a mouthful.
I know, right? But don't worry, we can simplify it. We isolate one of those square roots, square both sides, then do the same thing to get rid of the other square root. And we use our trusty C equals ARBA. After some algebraic magic, we get the standard equation. X y plus y plus y baller 1 I RBA. It's all spelled out in figure 11.27 if you want to see the details. The main idea is to get rid of those square roots and make the equation easier to work with.
All right, I'll trust you on that one. So XYY plus YRBPA means we have an ellipse centered at the origin with its major axis along the x-axis. What else can we tell from that equation?
Well, any point xy on the ellipse has to have an x-coordinate between day A and a y-coordinate between maybe B. Basically, the ellipse fits inside a rectangle with those dimensions.
What if the major axis is vertical along the axis?
Then the standard equation switches to x4BA2 plus AAO1. Remember, A is always the length of the semi-major axis, the longer one. So now A is under U because the ellipse is stretched vertically.
The source mentions that we're skipping ellipses that aren't centered at the origin or whose axes aren't lined up with a coordinate axis.
That's right. We're keeping it focused on the basics here, but one key thing to note. Ellipses are always symmetrical. They're symmetrical about both the x-axis and the y-axis.
So if we're looking at the equation, how can we tell which axis is the major axis?
Easy peasy. Just look at the denominators under x or b a well. The bigger denominator, that's a well. If it's under x or y, the major axis is horizontal. If it's under y, the major axis is vertical.
Makes sense. And just like the parabola, the ellipse also has a latus rectum.
It sure does. Just like before, it's the line segment that's perpendicular to the major axis, passes through one of the foci, and has endpoints on the ellipse. Figure 11.28 shows you what I mean.
How do we find its length?
For an ellipse with the standard equation xo plus yb is 1, the latus rectum has a length of 2b dot a.
Interesting. It uses both the semi-minor and semi-major axes. Where does that formula come from?
We can get it by taking the x-coordinate of a focus, which is C or AE, and plugging that into the ellipse equation. Then we solve for the I values, which gives us half the length of the latus rectum.
Time for some examples.
Yeah.
Example 9 says we got to find the foci, vertices, lengths of the axes, eccentricity, a latus rectum of the ellipse, given by x25 plus y9 equals 1.
Okay, the denominator under x, which is 25, is bigger than the one under 1, which is 9. So A equals 25, which means A is 5, and B equals 9, which means B is 3. And because A equals under x, the major axis is horizontal. To find C, we use C equals y, so that's 25, 9 equals 16. The square root of 16 is 4, so C equals 4. Now we can find everything else. The foci are at 6 AOC, so it takes 4. The vertices are at light A0, so an x of 5 0. The major axis.